Fundamentals of convection. This topic introduces convection as one of the main mechanisms of heat transfer in engineering systems. Convection always involves energy exchange between a solid surface and a moving fluid. The mechanism combines conduction effects near the surface and advection due to fluid motion. In many engineering applications, convection becomes the dominant mechanism compared to pure conduction. This chapter builds the conceptual foundation for quantitative convection analysis. Lesson Plan: Heat Transfer. This section places convection within the overall structure of the heat transfer course. The chapter sequence shows how conduction, convection, and radiation are systematically connected. Convection is discussed after students understand steady and transient conduction. With this structure, understanding of energy balances and temperature fields becomes more mature. The plan ensures a learning flow from fundamentals to advanced applications. Learning outcome. The learning outcomes emphasize physical, mathematical, and practical understanding of convection. Students are expected to distinguish between laminar and turbulent flows and their implications for heat transfer. Dimensionless numbers such as Reynolds, Prandtl, and Nusselt become the core of the analysis. The differential equations governing flow and heat transfer are introduced systematically. The final goal is the ability to use analogies and correlations to determine heat transfer coefficients. Heat transfer mechanisms. This slide compares conduction, forced convection, and natural convection in a single framework. Conduction occurs without fluid motion and is purely due to temperature gradients. Forced convection involves flow driven by a fan or pump, which accelerates heat transfer rates. Natural convection arises from buoyancy forces caused by density differences due to temperature. This comparison is important to understand the role of fluid motion in enhancing heat transfer rates. Heat transfer in parallel plates. The parallel plate system is used as a simple model to explain heat transfer through a fluid layer. The hot plate supplies energy to the fluid, while the cold plate absorbs that energy. The temperature gradient between the two plates becomes the main driving force for heat transfer. The thickness of the fluid layer strongly affects the magnitude of the heat transfer rate. This model is often used as a basis to understand conduction and convection mechanisms together. Velocity profile development over a blunt nose. The no-slip condition causes the fluid velocity at the surface of the body to be zero. Away from the surface, the fluid velocity increases until it reaches the free stream value. This transition region is called the velocity boundary layer. Streamlines show how the velocity profile develops around a blunt object. This concept is very important because the velocity distribution affects both friction and heat transfer. Check your understanding. Number 1. This slide serves as a short evaluation of the understanding of the no-slip concept. The core of the question emphasizes that the fluid velocity at the surface is zero. This is a fundamental assumption in real fluid mechanics. Without this assumption, the concept of the boundary layer cannot be properly explained. Such evaluations help strengthen conceptual understanding before moving forward. Fluid flow over a stationary surface. The flow approaches the plate with a uniform velocity before being affected by wall friction. At the plate surface, the fluid velocity drops to zero due to the no-slip condition. Away from the wall, the velocity increases gradually, forming a velocity profile. This profile changes along the flow direction because of viscous effects. This phenomenon is the basis of boundary layer formation in external flows. Contributions of Wilhelm Nusselt. Wilhelm Nusselt introduced the concept of dimensionless numbers that are crucial in heat transfer. The Nusselt number links convection mechanisms with conduction near the surface. His work also covered film condensation and laminar flow analysis in tubes. The mathematical approaches he developed became the foundation of modern heat transfer correlations. Until today, his name is always associated with practical convection analysis. Heat transfer through a fluid layer. Heat transfer through a stationary fluid layer can be analyzed similarly to conduction through a homogeneous medium. The temperature difference between the two surfaces becomes the main driving force for heat flow. The thickness of the fluid layer determines the magnitude of the thermal resistance. The thicker the layer, the smaller the heat transfer rate for the same temperature difference. This model helps bridge the understanding between pure conduction and convection. Forced convection in daily life. The example of blowing on hot food shows how forced convection works in daily life. The imposed airflow increases the heat transfer rate from the food surface to the surroundings. As the flow velocity increases, the thermal boundary layer becomes thinner. This causes the temperature gradient near the surface to become larger. As a result, the food cools much faster compared to natural cooling. Answer: B. Increased airflow enhances heat transfer through forced convection. Explanation of incorrect answers. A. Incorrect. Blowing relies on forced convection, not conduction alone, to increase heat transfer. C. Incorrect. Blowing enhances heat transfer by convection. It doesn't directly lower the food's temperature. D. Incorrect. Blowing introduces forced convection, which is distinct from natural cooling. A uniform flow approaching a flat plate is divided into a viscous region and an inviscid region. Near the surface, viscosity effects dominate and form a boundary layer. Far from the surface, viscosity effects can be neglected and the flow can be considered ideal. This separation simplifies the analysis of flow and heat transfer. This concept becomes the basis of almost all external flow analyses over flat surfaces. The flow around a ball shows flow separation that creates a wake region behind the object. After separation, the flow becomes irregular and forms a turbulent wake. The surface texture of the ball can affect the separation point and the size of the wake. This phenomenon is very important in aerodynamics and also influences heat transfer. The interaction between the flow and the object geometry determines drag and thermal characteristics. Flow regimes. Fluid flow can be classified into laminar, transitional, and turbulent regimes. Laminar flow is characterized by orderly motion with parallel streamlines. In the transitional regime, the flow begins to become unstable and shows small disturbances. Turbulent flow is chaotic with strong mixing and eddies. This classification is very important because it strongly affects friction and heat transfer. Thermal plumes around warm bodies. Schlieren visualization shows how warmer and lighter air rises around the human body. This phenomenon is called a thermal plume and is an example of natural convection. The air heated near the body's surface moves upward due to buoyancy forces. This process causes heat loss from the body to the surroundings. This flow pattern is important for understanding natural cooling and thermal comfort. Schlieren visualization shows the rise of lighter, warmer air near the human body. Velocity profile in a circular pipe. In the entrance region of a pipe, the velocity profile changes from uniform to developing due to viscous effects. As the distance increases, the flow reaches a fully developed condition with an unchanged profile. This region is called the fully developed flow region. The length of the entrance region depends on the Reynolds number and fluid properties. This understanding is important for analyzing pressure drop and heat transfer in pipes. Boundary layer development over a flat plate. This figure shows the development of the boundary layer from laminar to turbulent along the flow direction. Near the leading edge, the boundary layer is thin and the flow is laminar. After a certain distance, the flow enters a transition region and then becomes turbulent. The boundary layer thickness keeps increasing along the plate. This change in flow character strongly affects friction and heat transfer rates. Boundary layer development over a flat plate. The laminar boundary layer is characterized by smooth and orderly flow near the surface. After passing the transition region, the boundary layer becomes turbulent and shows strong mixing. The boundary layer thickness increases with distance from the leading edge. Near the wall, there is a very thin viscous sublayer that is important for momentum and heat transfer. This structure explains why turbulent flow usually provides higher heat transfer rates. Boundary layer formation. The boundary layer is formed because of the no-slip condition at a solid surface. The fluid velocity increases gradually from zero at the wall to the free stream velocity. The boundary layer thickness is defined as the distance from the wall where the velocity reaches 99% of the free stream value. This definition is conventional but very useful in engineering analysis. This concept becomes the basis for determining friction and heat transfer near surfaces. Temperature versus viscosity relationship. For liquids, viscosity generally decreases as temperature increases because intermolecular activity becomes weaker. In contrast, for gases, viscosity increases with temperature due to increased molecular activity. This difference in behavior comes from different momentum transport mechanisms in liquids and gases. This relationship is very important in flow and heat transfer analysis. Changes in viscosity directly affect the Reynolds number and the flow regime. Answer C. For liquids, viscosity decreases with temperature, while for gases it increases due to molecular interactions. Explanation of incorrect answers. A. Incorrect. This reverses the trends. Liquid viscosity decreases and gas viscosity increases with temperature. B. Incorrect. Gases exhibit increasing viscosity with temperature, not decreasing. D. Incorrect. Viscosity is highly temperature dependent for both liquids and gases, influenced by molecular behavior. Dynamic viscosities of fluids. This table shows that viscosity strongly depends on the type of fluid and temperature. Fluids such as glycerin and oils show very large changes in viscosity with temperature. Gases have much lower viscosities compared to liquids. This variation explains why flow behavior can be very different among fluids. Such data are important for practical calculations in flow and heat transfer analysis. Thermal boundary layer on a flat plate. The thermal boundary layer is formed because heat diffuses from the plate surface into the fluid. Within this layer, the temperature changes significantly from the wall temperature to the free stream temperature. Outside the thermal boundary layer, the fluid temperature is nearly constant. The thickness of the thermal boundary layer is not always the same as the velocity boundary layer. The relationship between them is strongly influenced by the Prandtl number. Contributions of Ludwig Prandtl. Ludwig Prandtl introduced the boundary layer concept that revolutionized aerodynamics. With this concept, drag forces on bodies can be analyzed more realistically. He also developed streamlining techniques for aircraft wings and air vehicles. His contributions extended to turbulence and supersonic flow theories. Almost all modern flow analyses are rooted in his ideas. Prandtl number ranges for common fluids. The Prandtl number represents the ratio of momentum diffusivity to thermal diffusivity. Liquid metals have very small Prandtl numbers because their thermal conductivity is very high. Oils and glycerin have very large Prandtl numbers because their thermal diffusion is slow. Water and gases fall in the intermediate range. This value determines the relative thickness of velocity and thermal boundary layers. Liquid metals have extremely low Prandtl numbers due to high thermal conductivity. Flow regimes of candle smoke. Candle smoke shows a visual example of the transition from laminar to turbulent flow. Near the flame, the flow is still smooth and orderly. Higher up, the flow becomes unstable and eventually turbulent. This change occurs because small disturbances are amplified by flow instabilities. This simple example helps in understanding the concept of flow transition in practice. Dye injection in laminar and turbulent flows. In laminar flow, the dye forms a smooth, straight line without significant mixing. In turbulent flow, the dye quickly spreads throughout the entire cross-section. This difference shows the very different levels of mixing between the two flow regimes. This visualization is often used in experiments to identify the type of flow. This concept is also directly related to the effectiveness of heat and mass transfer. Contributions of Osborne-Reynolds. Osborne-Reynolds introduced the Reynolds number to determine whether a flow is laminar or turbulent. Through pipe flow experiments, he showed how flow transition occurs. His work became the foundation of dynamic similarity theory in fluid mechanics. He also made major contributions to lubrication theory and mechanical engineering applications. Almost all modern flow analyses use the Reynolds number as a primary parameter. Reynolds number and fluid dynamics. The Reynolds number represents the ratio of inertial forces to viscous forces in a fluid flow. This value determines the nature of the flow, whether it tends to be laminar or turbulent. It depends on flow velocity, characteristic length, density, and fluid viscosity. If inertial forces are much more dominant, the flow tends to become turbulent. Therefore, the Reynolds number is always the first parameter checked in flow analysis. Effect of turbulence on heat transfer. In laminar flow, fluid particles are arranged in relatively orderly temperature layers. When the flow becomes turbulent, strong mixing brings particles of different temperatures into contact. This process accelerates heat transfer within the fluid. Therefore, turbulent flow almost always provides higher heat transfer coefficients. However, this enhancement is also accompanied by an increase in pressure drop. Answer B. Intense mixing during turbulence redistributes particles and accelerates thermal exchange. Explanation of incorrect answers. A. Incorrect. Turbulence disrupts thermal barriers, enhancing heat transfer rather than reducing it. C. Incorrect. Turbulence breaks down temperature layers, promoting mixing rather than organizing particles. D. Incorrect. Turbulence significantly enhances heat transfer by increasing convection, not leaving it unaffected. Velocity fluctuations in turbulent flow. In turbulent flow, the velocity at a point is not constant with time. The instantaneous velocity fluctuates around a mean value. The mean value is used in engineering calculations, while the fluctuations explain the chaotic nature of the flow. These fluctuations cause the intense mixing in turbulence. The separation between mean and instantaneous velocities becomes the basis of statistical analysis of turbulent flows. Velocity fluctuations and fluid motion. Velocity fluctuations cause fluid particles to move up and down across the flow cross-section. This motion carries momentum and energy from one layer to another. As a result, momentum and heat transport become much more effective. This is the main reason why turbulence enhances heat transfer. This phenomenon cannot be explained using simple laminar flow models. Velocity gradients in laminar and turbulent flow. In laminar flow, the velocity gradient near the wall is relatively mild. In turbulent flow, the velocity gradient near the wall is much steeper. A steeper gradient means higher shear stress at the wall. In addition, the turbulent boundary layer is usually thicker than the laminar one. These differences strongly affect both friction and heat transfer. Differential control volume in velocity boundary layer. A differential control volume is used to derive the mass conservation equation in the boundary layer. The dimensions of this control volume are dx in the flow direction and dy in the direction normal to the surface. The velocity components u and v are analyzed at each face of the control volume. With this approach, changes in mass flow can be systematically evaluated. This is the first step in deriving the boundary layer equations. A control volume is used for mass balance in the velocity boundary layer for 2D flow over a surface. Even though the flow is steady, the fluid velocity can change because of changes in cross-sectional area. When the fluid passes through a narrowing section, its velocity increases. This is an example of spatial acceleration, not time acceleration. The conservation of mass principle explains the relationship between area and velocity. This concept is important for understanding acceleration in boundary layers and internal flows. Differential control volume in momentum analysis. A differential control volume is also used to derive the momentum equation in the flow direction. Pressure forces act on the faces of the control volume due to pressure variations in the x and y directions. In addition, shear forces due to viscosity act on the top and bottom surfaces. By balancing all forces and the rate of momentum change, the two-dimensional momentum equation is obtained. This equation becomes the basis for boundary layer flow analysis. Boundary layer approximations. In the boundary layer, the main velocity component is the streamwise velocity u, while the transverse component, v, is much smaller. The most significant velocity and temperature gradients occur in the direction normal to the surface. In contrast, variations in the streamwise direction are relatively small and can often be neglected. These simplifications make the Navier-Stokes equations much simpler. This approach is essential for obtaining analytical boundary layer solutions. Energy and mass transfer in control volume. In a two-dimensional control volume, energy and mass can enter and leave through all sides. The mass flow must satisfy mass conservation under steady conditions. Heat flow must also be considered in both the x and y directions. By writing the energy balance, the energy equation for the thermal boundary layer is obtained. This equation links the velocity field with the temperature field. Boundary conditions for flat plate flow. At the plate surface, the no-slip condition states that the velocity components u and v are 0. The surface temperature is fixed at Ts, which is different from the free stream temperature T infinity. Far from the surface, both velocity and temperature must approach the free stream values. These boundary conditions are required to solve the boundary layer equations. Without proper boundary conditions, the mathematical solutions would not be physically meaningful. Answer: B. The velocity components u and v are 0 at the plate surface, indicating no relative motion. Explanation of incorrect answers. A. Incorrect. The no-slip condition means the velocity at the surface is 0, not equal to the free stream velocity. C. Incorrect. The velocity components at the surface are fixed at 0 due to the no-slip condition, independent of flow conditions. D. Incorrect. The velocity components u and v are unrelated to the thermal gradient. They are 0 due to the no-slip condition. Coinciding boundary layers, PR equals 1. When the Prandtl number equals 1, the velocity and thermal boundary layers have the same thickness. Under this condition, the dimensionless velocity and temperature profiles become identical. This greatly simplifies the analysis of convective heat transfer. This case is often used as an ideal model to understand the link between momentum and heat transfer. Although it rarely occurs exactly in practice, the concept is very useful theoretically. Similarity function for laminar boundary layer. The similarity function is used to transform partial differential equations into ordinary differential equations. The similarity variable eta combines the x and y coordinates into a single parameter. The function f describes the shape of the dimensionless velocity profile within the boundary layer. The first and second derivatives of this function are related to the velocity gradient and shear stress. This approach allows simpler numerical or analytical solutions. Non-dimensionalization. Before non-dimensionalization, many physical parameters are required to describe a convection problem. By non-dimensionalization, the number of parameters can be reduced to a few key dimensionless numbers. This process usually leads to the Reynolds and Prandtl numbers as the main parameters. This simplification allows the results to be generally applicable to many systems. This is why convection correlations are usually expressed in terms of dimensionless numbers. The non-dimensionalization reduces complexity, allowing universal application of governing equations. Temperature gradient and Nusselt number. The temperature gradient at the surface determines the conductive heat transfer rate near the wall. The Nusselt number links convective heat transfer to pure conduction at the surface. For steady laminar flow over a flat plate, this relationship can be derived analytically. A higher Nusselt number indicates more effective heat transfer. Therefore, the Nusselt number becomes a measure of convection performance. Nusselt number relationships. The local Nusselt number varies along the flow direction because of boundary layer development. The average Nusselt number represents the overall heat transfer performance of a surface. In general, the Nusselt number is expressed as a function of the Reynolds and Prandtl numbers. These relationships are usually obtained from experiments or numerical solutions. Such correlations are very important for practical engineering calculations. Reynolds analogy for Prandtl number equal to 1. The dimensionless velocity and temperature profiles become identical. Under this condition, the velocity and temperature gradients at the surface are also equal. The Reynolds analogy links the Nusselt number to the surface friction coefficient. This analogy shows the direct relationship between momentum transfer and heat transfer. This concept is very useful for estimating heat transfer from friction data. Answer B. It relates the Nusselt number, Nu, to the friction coefficient, Cf, for flow over a flat plate. Explanation of incorrect answers. A. Incorrect. The Reynolds analogy links velocity and temperature gradients at the surface, making them related. C. Incorrect. Velocity and temperature profiles are often linked and can be identical when dimensionless. D. Incorrect. Surface gradients are critical in analyzing heat transfer and cannot be ignored in the Reynolds analogy. Sir Thomas Edward Stanton. Stanton carried out extensive research on fluid flow, friction, and heat transfer. He also studied the effects of wind on structures such as bridges and roofs. His work contributed to the development of air-cooled engines and early aircraft designs. The Stanton number is named in honor of his contributions. His name is still used today in convection heat transfer analysis. Alan Philip Colburn. Colburn is known for his research on vapor condensation and heat and mass transfer. He combined momentum, heat, and mass transfer concepts into a single engineering framework. The Colburn J factor was introduced as a dimensionless parameter for heat and mass transfer correlations. This concept is widely used in heat exchanger design. His contributions helped simplify engineering calculations in thermal systems. The references are from Yunus A. Çengel and Afshin Jahanshahi Qajar, Heat and Mass Transfer, Fundamentals and Applications, McGraw-Hill Education.